Hey everyone, so in this video we're going to be talking about hypothesis testing, and this is going to be the second video on hypothesis testing. So just a review of what hypothesis testing is from the first video. Remember, we use hypothesis testing to objectively decide one way or another if our observations from a sample are significant enough to conclude whether or not a hypothesis about a population is true. So we have a hypothesis about some phenomenon. We go and gather some evidence, some data in the form of a sample, and then we perform this test to decide if the result is as significant as we originally thought it was going to be. So we develop a null hypothesis, which is denoted by HO or H0, and that's what we assume to be true until proven otherwise. And then an alternative hypothesis, which is what we're trying to test, and we test them against each other at a specified significance level, and we called this alpha. And then at the end of the test, we made two decisions, and remember, they were both based on the null hypothesis. We're either going to reject the null hypothesis, or we're going to fail to reject the null hypothesis. And the way we did this is by two different methods, and they were equivalent methods. One of them was the critical value method, where we determine the critical value, and if the test statistic falls outside of that critical value, then we determine that it's extreme enough to reject the null hypothesis. Otherwise, we're going to fail to reject it. And then we also had the p-value method, which is where we use the test statistic to calculate a p-value, and if the p-value is really low, that gives us evidence against the null hypothesis. And then otherwise, we would fail to reject the null hypothesis. And then we determined that we're going to get the exact same result whether we use the critical value method or the p-value method, and we looked at an image at the end that showed how they're directly related with each other. So now let's talk about hypothesis testing for proportions. So the idea itself is the same, except the numbers and the conditions are slightly different, just like before when we were talking about confidence intervals. So just like before, we need to have an independent sample. We need to have n times p0 greater than or equal to 5, and p0 is just going to be our hypothesized proportion. And then n times 1 minus p0 is also going to have to be greater than or equal to 5. And this is the same as before. This is just like our normality checking when we were talking about confidence intervals. So this is nothing new here. So if all these conditions are met, then we can use Z and perform a hypothesis test for the true proportion P. Now, the test statistic is something that we've seen before. We've seen this formula before. The only difference is going to be P0 instead of P. We're taking the sample proportion P hat, subtracting its theoretical mean, and dividing by its standard deviation. That's what we do when we standardize, and it's no different here. So it's going to be P hat minus P0 over the square root of P0 times 1 minus P0 over n. So let's look at an example. So a baseball scout is interested in a young prospect, but the scout wants to make sure it's worth spending the time and money to go see the player play. And the scout says, well, I'm not going to waste my time if the player doesn't have a batting average over 300, which I'm a baseball fan. And if you're a baseball fan, you know that this isn't exactly how it works, but we're going to use this as an example just for the sake of simplicity. So anyway, so far this season, the players recorded 57 hits in 150 at-bats. So what we need to determine is, should the scout go see the player? Or in other words, do we have enough evidence to suggest that the player's true batting average is above 300? And here we're told to use 10% significance. So As always, I always recommend listing any of the information that you have just so you have it available when you need it. So we're told that x in our proportion formula is going to be 57, and n, which was the number of at-bats, was 150. So when we calculate our sample proportion, we're going to get 57 over 150, and we're going to get a 380 batting average in 150 at-bats, which is pretty darn good. Now, what we're testing against, our hypothesized proportion, is 300. We're testing whether or not the batting average is above 300. So that's going to be our P0. And our alpha level is based on our significance level. And we were told to use 10% significance. So that means our alpha is going to be 0.10. And here we're going to assume an independent sample, which in other words means that the result of one at bat isn't affected by the result of the previous at bat. So we're just going to assume that's going to be true, otherwise we wouldn't be able to carry on with this test. So we have n times p0, which is one of the normality checks we have to do, which is 150 times 0.3, and that gives us 45. And then n times 1 minus p is 150 times 0.7, and that gives us 105. So all of our conditions have been met here, and now we're allowed to carry on with this test. So this is how we're going to structure the test here. We have the null hypothesis, which is a statement of equality, and this is what we're going to assume to be true unless we have enough evidence to say otherwise. So in this case, we're assuming the true proportion, or the true batting average, is 300. And what we're testing for is whether or not the true batting average is greater than 300. Now, since this is a greater than sign, this is going to be a right-tailed test. And since this is a one-tailed test, we're going to have all of that alpha in that right tail. And when we determine the value of z that gives us an area of 0.10 in the right tail, we'll find that our critical value is going to be 1.28. So what that means is we will reject if our test statistic is greater than 1.28, because then it will be more extreme than our critical value. So now let's calculate our test statistic. This was the formula that we had before, and if we plug everything in, then we'll get 380 minus 300 over this mess right here. And if we do this math, we'll get 0.08 over 0.0374, and that will give us a test statistic of 2.14. Now, we already know just by looking at this that that's more extreme than this. It's greater than 1.28, so we know we're going to reject before we do anything else. But just for the heck of it, let's calculate the p-value here. So the p-value is the probability of observing something as extreme or more extreme than what we saw. So in probability notation, that's going to be the probability that z is greater than 2.14, our test statistic. And remember, to flip the inequality here, we have to subtract from 1 to make this quantity able to be looked up on the table. And when we do that, we'll get 1 minus 0.9838, which gives us 0.0162. Which, remember, our alpha level is 0.10, and our p-value is 0.0162, which is lower than alpha. So that means we're going to reject HO. So that means we have enough evidence to suggest that the player's true batting average is above 300, and now we can tell the scout that he can go see the player play, because we've determined that it's very likely that this player's true batting average is higher than 300. So let's look at an image of what we just did here. So we had an alpha level of 0.10 that was given in the problem, and we had to find the value of z that gave us an area to the right of 0.10. And it turns out that that value of z is 1.28, and that's what we used as our critical value. And the critical value is what sets the border between the rejection region and what's not in the rejection region. So then what we did is we found a test statistic using our sample, and we said to ourselves, okay, our test statistic is 2.14, and this falls in that rejection region. So that tells us that we're going to reject the null hypothesis. And just like how the critical value and alpha are related, the test statistic and the p-value are related. So that's why every time we get a test statistic that falls in this rejection region, we're also going to get a p-value that's less than alpha, because the p-value represents the probability of observing something as extreme or more extreme than what we just saw. So in other words, it's the area to the right of the test statistic in this case. And if this was a left-tailed test, it'd be the area to the left of the test statistic. So now let's talk about two-tailed tests. And two-tailed hypothesis tests come into play when we're interested in testing whether a mean is different from or not equal to a hypothesized mean. So an example of this would be something like this. And notice this looks the exact same. The only real difference here is this right here, this not equal to sign. So before we were working with a less than sign or a greater than sign here, and the less than sign tells us that we're going to have a left tail test, and the greater than sign says we're going to have a right tail test. But here, this is not equal to, so that means we can have evidence in the left tail or in the right tail. So that means we're going to have a two-tailed test. So what that means for alpha now is that means alpha is going to be split up into the two tails. So instead of having alpha all in one tail, we're going to have half of alpha in the left tail and half of alpha in the right tail. So here's an example of what this looks like. So normally we had the rejection region all in one tail, but now we have to split this up into these two tails here. So the area to the left of this critical value right here is 0.025, and the area to the right of this critical value right here is also 0.025. And when you add them together, you're going to get 0.05, which would be our alpha in this case. Now, the other thing to notice here is that these values right here should look pretty familiar to you, because we used 1.96 when we were constructing a 95% confidence interval. And in fact, this is the same logic. We're coming up with a value of alpha, we're cutting it in half, and we're determining the values that give us an area outside of that region. And this is the same kind of logic we're going to be using for our hypothesis test. So this is an example with alpha equal to 0.05, but it's all in the left tail. Now notice how this area is larger because we're not splitting it up into two tails, and that means our critical value is also going to change. So if I flip back and forth between these, you'll see that this area gets split up into the two tails, and that's the difference here. So keep in mind that since alpha is being split up into the two tails, we're going to have two critical values here, like I talked about before. We're going to have z alpha half and negative z alpha half. So what that means is that since we're not specifying our direction, we're going to need to have more extreme evidence than we would have if we were conducting a one-tail test. So what this means for the p-value is that we actually need to double it. And the reason why we need to double it is because with the p-value, we're interested in the probability of observing something as extreme or more extreme. And if we don't double it, we're only considering one of the tails. And to consider both of the tails, since this is a two-tailed test, we have to double it. So let's look at an example. So suppose a potato chip company wants to test whether or not their 8-ounce bags of chips, the ones that are labeled as 8-ounce bags, are actually 8 ounces. So they gather a sample of 49 bags and they find that the mean weight from the sample is 7.89. And then from past tests, they found that the standard deviation is zero point 0.4 ounces, and we're just going to assume that that's going to be the population standard deviation. So what we need to know is there any evidence to suggest that the mean weight is different from 8 ounces? So this might be important to them because if the weight is too small, then that means they're not advertising their product correctly. And if the weight is too big, then they might be able to take some potato chips out of the bags and still justify calling them 8-ounce bags, and that saves them money. So we need them to be close to 8 ounces. So this is a very relevant test to do. So again, first thing we're going to do is we're going to list out the information that's given to us. So in this case, we tested 49 bags of chips, so N is 49. Our sample mean from those 49 bags was 7.89 ounces, and we're going to assume the population standard deviation, sigma, is zero point 0.4. And now we can get into the structure of our hypothesis test. And remember, the null hypothesis is always going to be a statement of equality. And we're testing whether or not this population mean mu is 8 ounces. And our alternative hypothesis is going to be that the mean weight is not equal to 8. And since there wasn't a significance level given to us, we're going to assume that alpha is going to be 0.05. So now we can carry on with our test. So since alpha is equal to 0.05, the critical values are going to be negative 1.96 and 1.96, just like the image we looked at earlier. And that means we're going to reject the null hypothesis if the absolute value of z is greater than 1.96, which is just a fancy way of saying that if the value of the test statistic is more extreme than the critical value, then we're going to reject the null hypothesis. This is nothing new. So the test statistic here is the same old formula we've had from before. We take x bar minus the hypothesized mean, divide by sigma over the square root of n. And when we do that, we're going to get negative 1.93. Now, before we do anything else, we already know that we're not going to reject the null hypothesis. And we know that because our critical values were negative 1.96 and 1.96. And this is not more extreme than those. This doesn't fall outside of those values. So using the critical value method, we see right away that we're going to fail to reject the null hypothesis. But I want to continue using the p-value method here because there's an important point that needs to be made. So if we were to use the p-value method, we would need to be a little bit careful because the area to the left of our test statistic, negative 1.93, is 0.0268. And if we had stopped there and compared it to alpha, we would see that it's less than alpha. And the conclusion we would have come to is that we needed to reject the null hypothesis, which is not the correct decision. And the reason this isn't the correct decision is because we did not double the p-value like we should have. But when we do double the p-value, we're going to come up with 0.0536, which is greater than alpha. So this matches our conclusion from the critical value method here. So that's why it's important to double the p-value when you're doing a two-tailed test. And since we're failing to reject the null hypothesis, There's not enough evidence to suggest that the mean weight of the potato chip bags is different from 8 ounces. So, in other words, this potato chip company could probably just continue doing what they're doing because there's not enough evidence to suggest that the mean weight of the potato chip bags is different from 8 ounces in one direction or the other. So, now let's start talking about hypothesis testing using T. So, the nice thing is that the process is pretty much the same with T as it is with Z. And the only small difference here, which could cause us some problems, is that the tables are structured in different ways. Remember, with the Z table, we had the critical values on the outside of the table, but instead, with the T table, the critical values are on the inside of the table. What that actually means is that those values that we're using on the Z table to find P values are on the inside of the table, but with the T table, we aren't going to be able to find exact P values because we don't have this large table of exact values. So we'll look at an example of this in a little while. So an example here, so suppose Jane has been running a lot lately and she's interested in seeing if her time is improving for running the mile. She wants to know if her mean time is less than 9 minutes. So she tests her improvement by running a mile for 9 days in a row and finds that her mean time for those days is 8.75 minutes or 8 minutes and 45 seconds. And the standard deviation is a quarter of a minute or 15 seconds. So, assuming her times are normally distributed, has her mile time improved? And we're going to be using a significance level of 1% or an alpha level of 0.01. So, when we list out our information, she did 9 runs for 9 days, so n is 9, and her mean time for those 9 days was 8.75, and the sample standard deviation was 0.25. And our hypotheses here, we're assuming that her mile time is going to be equal to 9. That's our null hypothesis. And she's interested in seeing if her time is improving for running the mile. And what that means is that we're testing whether or not her time is now less than 9 minutes for running the mile. And we're going to be using a significance level of 0.01. So remember, n was equal to 9. So that means df is going to be n minus 1, which is equal to 8. So we're going to have 8 degrees of freedom. And if we look this up on the t table, we're going to come up with a critical value of negative 2.89. Now, what we actually have to be careful with here is what you're going to find in the table is 2.89. But since this is a left tail test, we have to make this negative to consider the negative side of the t distribution. And when we calculate our test statistic using the same formula as before, we'll come up with a test statistic of negative 3. And that's less than the critical value of negative 2.89, which means that it's more extreme. So that means we can reject the null hypothesis. And that means that we have enough evidence to conclude that Jane's mile time has gone down, which means it has improved. So the critical value method, as we see up here, is the same process as the critical value method when we're using Z. But where we run into problems is when we're using the p-value method. And we could have used the p-value method, and in fact, the p-value method is what's used more commonly in practice. But when we're restricted to using just the table, we can only find intervals for p-values. So here's an example of what I'm talking about here. So our test statistic was negative 3, and we had 8 degrees of freedom. But the t table only gives us the positive values of t, only the right side of the t distribution. So what we can do is we could look up t equals positive 3 on the table as if it were a right tail test and then use the symmetry of the t-distribution to turn this into a -3, and the same thing would hold for a left-tailed test, which is what we're doing. And when we try to look this up on the table, we first find 8 degrees of freedom, and then we'll notice that we can't find 3.00 in this row anywhere. But the best thing we can do is to find a value just below it and then a value just above it. And what that does is it gives us bounds. So the p-value that's associated with 2.8965 is 0.01. And the p-value that's associated with 3.3554 is 0.005. And we know t equals 3 is somewhere in between these two values. So what that tells us is that the p-value is somewhere in between these values. So we know the p-value is somewhere in between 0.005 and 0.01. And in fact, if you're using software, which is why the p-value method is more commonly used in practice, we have computers to tell us what the exact p-value is. If you're using software, the exact p-value is 0.0085, and that's less than alpha. So that means the p-value is less than alpha, and the null hypothesis can be rejected. And now you're probably saying, like, well, we don't have software available to us, so how do we know if the p-value is less than alpha? Well, we know that the p-value is less than 0.01 and greater than 0.005 based on these bounds that we found up here. But all we really care about is whether or not it's less than 0.01, which we determined it is. So even though we don't know the exact p-value, we do know that it's less than 0.01, so that means our p-value is less than alpha, and that's all we really cared about. So that's how we know that we're going to reject the null hypothesis here. So anyway, that's all for this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.